3, 2, 1.
Assalamualaikum to our respected lecturer, Mrs. Rohana Ismail, and we are from Group 1, and today we are honored to represent our project titled Student Record Search Optimization. It is developed for the subject algorithm design and analysis. Let's begin with the purpose of this project. The main aim is to enhance the way universities manage, track and report academic data by making student record searches more efficient. Now, onto the problem we are addressing. As the volume of student data increases, retrieving information quickly becomes a challenge. This inefficiency can disrupt administrative and academic operation, which rely heavily on fast and accurate access to the records. Our focus is on comparing 4 search algorithms. The first one is linear search, binary search, hash table search, and the last one is B3 search. This will be evaluated based on 3 key aspects. First one is time complexity, and then space usage, and how suitable each is for academic system. The main goal is to determine which algorithm performs best under different student data condition and usage needs. Finally, here are our objectives. First, to examine how compatible each algorithm is with typical student record systems. Second, to provide a comparative analysis of their performance. And third, to offer practical recommendations that universities can apply in real-world scenarios. This sets the stage for the rest of the report. Okay, before we jump into the methodology, I will generally brief about the algorithm that we have selected. Our group selected 4 commonly used search algorithms that represent different approaches and efficiencies. First one is linear search, a simple method that checks each record sequentially. And binary search is a more efficient technique that works only on sorted data. And the third one is hash table search, that ideal for fast exact match lookups using a unique key. And the last one is B3 search, a balanced tree structure used in databases that support both exact and range-based queries. Each algorithm was analyzed in detail to understand how it performs in different use cases relevant to student records.
Now let's begin with the linear search algorithm. For the linear search, is operate by checking each element in the list one by one until the target value is found or the end of the list is reached. It does not require any sorting or special data structure. For our context, the linear search is most useful when student records are stored in unsorted or sequential files, such as temporary logs or backup data. It may also be used during the early development phase of system before data indexing is implemented. Okay, now for time complexity, we use big O notation, which stands for order of, to describe how the algorithm scales with input size. For the best case, big O1 if the record is found at the very beginning. For average case, big O and divide by 2, which is approximately big O(n). The worst case is big O(n) when the record is lost or missing. For the space complexity, big O1, since it does not require any additional memory beyond a few variables. While linear search is easy to implement and understand, it becomes most inefficient for large data set. Therefore, it is best suited for small, unsorted data collection or system where search frequency is low.
Binary search, a much faster algorithm under the right conditions. So how it works? Basically, binary search works only on sorted data. It starts by examining the middle element of the datasets. If the target is smaller, it will search the left half, and if the larger, it will search on the right half. This process repeats until the item is found or the range is empty. Applications in our case study. In educational system, binary search is suitable for static databases where student records are sorted by ID or registration number. For example, if the system needs to retrieve student ID 2025101123 and the database is sorted, binary search offers a quick solution. For time complexity in binary search, best case O1 if the target is exactly in the middle, average and worst case O log n since each step cuts each space in half. Space complexity O1 in iterative form and O log n if implemented recursively. So the trade-off in binary search, the major limitation of binary search is that the data must be kept in sorted order. In systems where frequent updates or insertions occur, maintaining this order becomes costly. Therefore, it is most effective in systems where data is rarely updated but frequently read.
Now, let's move on to hash table search, which is known for its speed and efficiency. How it works. This method uses a hash function to convert a unique key, like a student ID or email, into an index. The algorithm then uses this index to directly access the corresponding record. If multiple keys map to the same index, collision resolution technique like chaining are used. Application in our case study, hash table search is ideal for real-time portal where fast access is needed, such as student login system or profile lookup by ID. Time complexity based on average case 0-1, assuming a good hash function and low collision. Worst case 0n when collisions are too frequent, and space complexity 0n due to extra space needed for the hash table and collision management. Trade-off: hash tables are excellent for exact match queries. However, they are not suitable for range queries like find all student with GPA above 3.0. Performance depends heavily on the design of the hash function and the load factor.
Okay, now I will be explaining how bit research works and why it is a powerful tool, especially in large-scale data systems like student information databases. Let's start with the basics. A B-tree is a self-balancing tree data structure that keeps data in a sorted order. Unlike hash tables, B-trees can handle both exact match queries and range-based searches. This makes them ideal for situations like if you have to list all computer science students with a GPA above 3.5, something hash table might struggle with. Now, how does B-tree works? Each node in a B-tree stores multiple keys and pointers. This helps reduce the number of reads, especially when working with disk-based storage. It balances itself automatically, which means the tree remains shallow and searches remain quick, even when the dataset grows large. In terms of time complexity, B-tree performs consistently well. Whether it is the best, average, or worst case, the search operation always takes O log n time. This is thanks to its self-balancing design. Now, we move out to the space complexity. The space complexity is On, which means the space it takes grows linearly with the size of the dataset. This is because each node can store several keys and pointers. Now let's talk about trade-off. Yes, B-tree might have a slightly higher memory overhead compared to hash tables. This is due to the extra pointers and balancing mechanism. But in return, we get several advantages. First one is they are very stable across different types of query. Second one is they support multi-criteria and range searches. The third one is they work extremely well on secondary storage like this. All of this makes B-tree search perfect for databases that need scalability, consistent speed, and flexible queries. So, in summary, B-trees are a better choice for systems that need flexibility and reliability in handling complex queries.
Comparative analysis. To summarize all four algorithms, first is linear search. Linear search is best for small or unsorted dataset and simple to implement but inefficient for large data. Second is binary search. Binary search is ideal for read-heavy system with sorted static data and fast performance but requires pre-sorting. Third algorithm is hash table search. Hash table search is excellent for exact match queries like searching by ID and offer constant time lookup but not suited for range search. Fourth algorithm is bit research. Bit research is suitable for range queries and large disk-based dataset and maintains logarithmic performance even with frequent updates. Each algorithm offers different advantages depending on the size of the dataset and the nature of the search operation.
In conclusion, there is no one-size-fits-all solution. The choice of search algorithm should be based on three things. The first one is the type of queries to find the exact match, exact different match and range. Second of all, the size of student record database. And lastly, how frequently update of the data. When you want to use for small or simple system, the linear search is your answer. For sorted static data, use the binary search because it is fast and efficient. For real-time exact match system, the hash tables are the best choice. And when you want to use for large-scale flexible system, the B trees provide the best balance of performance and capability. When understanding this algorithm, it helps the universities build more efficient, responsive, and scalable academic platform.